Thank you. I wanted to explain the title one more time. Originally, I was implying that I've been doing this for 35 years, and I've been talking about it off and on for 35 years, so this is one more time. But actually, we had a very good introduction to some of the things I've been going to talk about on the previous paper by Gary van der Hagen, so maybe this is just a sequel to his talk. So maybe that's what one more time means. Okay, just a very brief review of some of the advantages of photon counting. I understand there's disadvantages too, but the first thing is near theoretical performance. That means, to me, that means that if you can count all the photons that are coming into the telescope in the bandpass that you're interested in, you can do no better than that. So the PMTs these days certainly don't count all the photons. There's a quantum efficiency of only 25% or so, but the noise is essentially zero, so you can get near theoretical performance on that basis. The second point, I think, is even more important: the high bandwidth information, and by that I mean that, as Gary pointed out in the last talk, that if you take faster and faster samples, you get more noise just from the statistics. But from the system itself, it's basically noiseless, and so you can sample it at a few microseconds per sample, and then later on decide, well, I really want to add those up to a millisecond or 10 milliseconds per sample, and you're not adding any noise to the observation. And that's a very important point, and I'll use that later on in the talk. And finally, the detected signal starts out as digital data, so you can immediately apply digital filtering, low pass, high pass, and FFT analysis, or you can digitally rebin them to whatever level you want. Okay, let's see, that's the right button. Okay, this is some early data. Like I say, I've been at it for 35 years. This is AM-HER, which some of you may be familiar with. It's about a 13th magnitude star, and it flickers away because it's a cataclysmic star, which material is falling off of the secondary onto the primary, and it's not forming an accretion disk because it's a polar, meaning that it has extremely intense magnetic field that funnels the material right onto the star, and so it generates not only optical flickering, but X-rays as well. So it's an interesting star to watch. It's flickering most of the time, and so this is about an hour's worth of data, 2 seconds per sample. Just an old photon counter that I had back in the 80s. I'm really pleased with this data. HTCAS has rare super outbursts. This is one of the rare super outbursts. It's a cataclysmic star, and every hour and I think it's 7 minutes, the two stars orbit around each other, and you can see the eclipses. The deep eclipses are where the primary is covered and most of the accretion disk is covered, so you have deep eclipses, unlike a lot of cataclysmic stars that don't eclipse. And then in between we have the super humps. Well, you can see them, and they're actually moving through the light curve. They're not actually sharing this, as was mentioned yesterday several times. They don't actually share the same orbital period as the two stars around each other. So this is like I say, a rare opportunity to catch this thing at a super maximum. Okay, these first two old. The reason I'm showing these first two old data sets is that it used to be a useful thing to use photon counting for this. Now, of course, you can do much better with CCD because you don't have the gaps in the data while you go off and look at a comparison star, look at the background, take a background reading. You can monitor it continuously, and plus you have a more quantum efficiency with a CCD and a wider bandpass. So for second integrations or 10-second integrations or whatever, these days I'm sure you'd want to use a CCD. The next picture shows an occultation, which again Gary introduced very well early before lunch. And this is when the moon was moving through the Hyades in 1979, and I caught a nice bright star, and you can see the diffraction pattern. And if the star has any significant diameter, you could infer that from that. I haven't tried to do that, but this is more of a photon counting strength, which is high data sampling rate. So here I'm sampling the photons every millisecond, and you can see it gives a nice measurement of that diffraction pattern. The next one is also a millisecond, and this is a double star that I didn't realize was a double star, binary. You can see that it has a diffraction peak before each of the stars disappears, and the separation there corresponds to about 4/10 of an arc second. This is a binary that goes from 4/10 to 4/100 of an arc second, so most amateurs aren't familiar with this one, but again, photon counting does a good job, and this is back in the old days. You could do very high-speed work. Okay, what's new? At least new for me, is that you now have the photomultiplier systems integrated with the high voltage supply and the amplifier discriminator. So you just have a single box that you give 5 volts and out come photon pulses. That's a big step from the old days where you had to have high voltage supplies and adjust the amplifier discriminator. And so this is a really simple thing to use in terms of getting photon pulses out. The other thing the second item there is we now have high-speed counters as PC boards. And again, I spent a lot of time building my own high-speed counter in the old days, but you can, the system I have now has 8-channel high-speed counters which can handle a pulse per separation of about 15 nanoseconds, which is better than the tube. So I can put in several different channels of photometry simultaneously sampled at whatever speed I want to sample them. And you can also stick in the PPS of a GPS sensor, so you can get timing to on the order of a millionth of a second if you wanted. You get GMT to a millionth of a second. So this is a major step forward, the fact that these PC boards that you can buy and you can do good photon counting as a result. And finally, of course, PCs themselves are doing much better. You can do literally a billion data point file. Okay, this is a picture of the module. Again, I just have a simple 5-volt regulator there as the only power that goes in, and the photon pulses come out. And this is my telescope. Incidentally, this is a telescope I've had for 40 years, and it was originally on the roof of Rand Corporation in Santa Monica, and it's a cave 16-inch, and all of the data, including the recent data, was taken with this thing. You can see the little right there, the little photon counting module, which is really tiny relative to everything else. And so we're selling the wrench, including this telescope and observatory. If anybody's interested, contact me afterwards. That's a plug. Okay. The new system then, what do you do with it? In fact, I want to go back and before I talk about that data. What I've done, the rest of the paper, I've taken very rapid samples of whatever star I'm looking at, whatever object I'm looking at, whether it's a bright star or a 15th magnitude star. And I sample it at 3 microseconds per sample, which is ridiculously oversampled for anything that we know about. But again, you can recombine all that data. You can rebin it to whatever integration time you want. So just an example of this next one is a bright star, 21 Lyra, which as far as we know is constant. And you can see this is 96 microseconds per sample. So we've got 10,000 data points there, and goes on. The file goes on for a long time. And you can see two forms of noise there. And I want to emphasize that all of this noise is associated with the photons arriving at the telescope. Nothing is introduced by the system. The dark current is essentially zero. And so this is a very bright star, and you can see the low frequency noise is due to seeing, and the high frequency noise, the point to point, is simply the arrival of the photons at the telescope, and those vary depending on, that's just a statistical variation, or also known as shot noise. Now, what you can do with this is you could filter it with a low pass and take a look at the low frequency variation of the atmosphere if you wanted to, or you could do a high pass and look at everything that's not affected by the atmosphere, and that's what I did in the next frame. And so you can see that this is the same data, same sample, and I've taken something like 300 hertz and lower and removed it, and so you see that this is just strictly shot noise. There's no, as far as we know, there's no signal in there, but I'll show a signal later. And so you can see that the zero is now, the level is now zero because one of the frequencies that was filtered out was DC. So it's, you can look for higher frequency signals if you like with this data. Okay, another thing you can do is FFT filtering. This shows the same data resampled at 768 microseconds per sample. And again, well, you can see this is a power spectrum, so this is power in dB on the vertical axis and frequency up to 500 hertz on the horizontal axis. And what we see is, what we expect to see is the power going up just from the atmospheric effects, because this is a constant star as far as we know. And then there's also a level of power at the floor is determined by shot noise, and that's a constant level. It doesn't matter how far out you go, you have a constant level of noise. That's why it's also known as white noise. It's frequency independent once you get rid of the signal, which is the atmosphere in this case. Okay, well, another thing you can do is resample the data and look at a different frequency band. And so I took the same data and resampled it to a shorter time, so that gave me a higher frequency. So this is a frequency plot out to 2 kilohertz, and again the atmosphere comes roaring down here at low frequencies, and you can see it's just gone by 200 hertz. There's no trace of it on the rest of the way out. And then of course I have my little green min signal here, and that was a surprise the first time I saw it, because I didn't put a little green min in there. And it turns out that for very, very bright stars, there's some resonance in the system, which, the way I found this out, I looked at several bright stars, and they all had a resonance of around 800 hertz. It moved around a little bit, but depending on how bright the apparent brightness was. So this is kind of an upper limit of brightness, because I'm starting to see some kind of resonance in there. If there were a real signal, it could be a broad peak, or it could be a sharp peak like that, and it would be very exciting. Okay, so what else can we do with data that you've sampled at a very high rate? You can look for pulses, and this is just a program that I wrote that searches the data for any pulse. It finds the largest pulse in the data set, then it bins then all the data by a factor of 2 and goes through and looks again for find the largest pulse. So keeps doing this, making longer and longer samples through the data, so that if you have a pulse that's long and low amplitude, it'll pick it up after it's binned a lot of data samples together. Or of course, if you have a sharp pulse in the beginning, it'll at a very high frequency, you'll find that. So what does this do? I started out with a faint star, which actually is the sun, highly filtered version of the sun, because I wanted to get rid of most seeing effects. So this is actually a very highly attenuated sun. And this shows the bin ratio is the ratio. I started out with 1, which was 3 microseconds per sample. bend it together to 6 microseconds, then 12, and on up until it was bend ratio was 8,000, 2 to the 13th. And each time look for the highest pixel, the highest peak in the sample. And actually, I do 2 passes for each bending to get a stagger in there, and I got something like this. And okay, you look at that and say, that's wonderful. What does that mean? You expect to get bigger peaks as you put more and more data together. You get more and more a bigger sample, a bigger signal per sample, and so eventually it rises up. Well, you can calculate, assuming that this is strictly statistical data. You can fit it with a Poisson curve. Oh, let's see, press this thing, and lo and behold, if you do the red curve is a Poisson distribution, it does an excellent job of showing that this is strictly random data, and that's good because it was just taking attenuated sunlight. At the very low bend ratios, I don't know why it hangs off at 4 counts per, or 5 counts per sample, but it does. But basically, this gives you a very sensitive thing. If something is raising, if you have a signal that's above the what you'd expect from a strictly random distribution, then it should rise above the red line significantly. And lo and behold, I have a case like that. This is my friend A.M. Herr. I looked at A.M. Herr several times with this high frequency sampling and didn't see anything. But this one time, the signal is, I don't know how to do this. Oh, there it is. The signal is so much higher. This is a factor of 2, and a factor of 2 above Poisson in this case is just gigantic. It couldn't possibly happen statistically. And you can see also that it's sampled at several different bend ratios, which means it's a broad high peak. So something's going on in the data. And so then I looked at the actual time series. I rebend it to 3 milliseconds per sample because that was kind of the peak of that. Right here, how do I point at this thing? Anyway, right in here is about 3 milliseconds per sample. So that's kind of the peak, and so that's why I bend it at that level. Whoops, bend it at that level. And there's these 2 monster pulses. Now these are not statistical pulses. These are definitely optical pulses. The only thing is, I have the same problem that Gary mentioned. When you start seeing things at this time resolution, you don't know where they came from because you can't look at it with your eye and say, oh yeah, that's what happened. So this could be an airplane flying by. It could be a satellite, or a couple satellites, I guess. Or it could be lightning flashes, although it was a clear and cloudless night as far as I know. Or it could be some other kind of flash. So that's a problem you get into. You see things which you don't expect and that are really could be very significant if they're actually coming from A.M. Herr. But I can't prove that they're doing it. So that's the next go around is a photometer that will look in the periphery around the signal. So if there's a flash or if there's a satellite coming through, it will see it around the periphery of the detector. Okay, so I think I'm just about out of time, so I'll just close with this quote from Jocelyn Burnell, who discovered pulsars, and I'm sure many of you know that story, but this is a speech she gave not too long ago. We have neglected, incidentally, time variability. The X-ray astronomers are alert to it, radio pulsar people are alert to it, gamma ray astronomers are too, but only now are optical astronomers starting to study things that go bump in the night. And as the previous paper discussed, buzz in the night. It's a fascinating and under-researched topic, and I think that it's an area that if amateurs are interested in, the hardware is certainly there. You can build up a system relatively cheaply to me, the biggest challenge was writing all the software to look at this data. Okay, that's what I have.